I'm Dr. Eleanor Martin, Assistant Professor in the University of Oklahoma's School of Meteorology. And today I'll be discussing feedbacks within the global energy budget. The globally average temperature of the Earth is determined by the balance of incoming shortwave radiation from the Sun and outgoing longwave radiation from the Earth. When we add a greenhouse gas, like carbon dioxide, to the atmosphere, the amount of incoming radiation remains the same, but the outgoing radiation from the Earth is reduced. This imbalance leads to an increase in temperature in the atmosphere and at the ground. However, this temperature increase leads to other impacts in the climate system that can then affect the global energy balance. Subsequently, these impacts then cause further changes in temperature. This connection between a system's output and its input is known as a feedback. Feedbacks can be positive or negative. Positive feedbacks amplify the temperature effect of changes in greenhouse gases and result in greater warming. Negative feedbacks diminish the temperature effect of changes in greenhouse gases and result in less warming. The climate system contains several well-understood feedbacks that are important in understanding climate change. The first feedback I'll examine is the water vapor feedback. This is a positive feedback, so it acts to further increase temperatures caused by the addition of greenhouse gases like carbon dioxide. A basic physical property of the air is that as temperature increases, more water vapor can exist in the air. Often this is thought of as the air holding more water vapor when the temperature gets warmer. This property is the key to understanding the water vapor feedback. We begin with increased temperature due to the addition of carbon dioxide to the atmosphere, as we've already discussed. In this warmer world, we have more evaporation from the oceans, rivers, and lakes. In addition, the warmer air is able to hold more water vapor. Water vapor is also a greenhouse gas, so more water vapor in the air means less outgoing radiation is able to escape to space, and an even larger imbalance in our global energy budget. This imbalance causes temperatures to increase further, so the air can hold even more water vapor, and so on. This is a positive feedback loop. The water vapor is a primary reason that Venus has a surface temperature of around 872 Fahrenheit. A second example of a positive feedback is the ice albedo feedback. Albedo describes how reflective a surface is to the incoming radiation from the sun. Ice is very reflective, and so it has a high albedo. Forests and asphalt are not very reflective. They absorb most of the radiation that reaches them, so they have a low albedo. In a warmer world, due to the addition of carbon dioxide, we have less ice and snow as the warmer temperatures cause melting. With less ice and snow, the albedo, or reflectivity, of Earth will decrease. This means that the Earth will be absorbing more radiation from the sun, so our energy budget is out of balance, and the temperature will increase further, melting even more ice until eventually no ice will be present on Earth. This positive feedback is very important for the current climate, but is also vital to understanding ice ages. I've discussed two very important positive feedbacks, water vapor and ice albedo, but negative feedbacks also occur in the climate. The most important negative feedback that regulates the Earth's temperature is the dependence of the outgoing long-wave radiation on temperature. Every object with a temperature, including you and me, emits radiation. And the higher the temperature, the more radiation is emitted. So when the planet warms up, it radiates more heat back out to space. When there is more energy out than in, the temperature cools to balance the energy budget. So this negative feedback works to keep our Earth's temperatures from getting uncontrollably hot or cold. Scientists understand the water vapor, ice albedo, and outgoing long-wave radiation feedbacks very well. But there are many feedbacks in the climate system that we understand less, and some we may not yet know. For example, the feedbacks associated with clouds are not as well understood as those we've already discussed. A warmer atmosphere produces more low clouds, which reflect more radiation out to space and reduce the temperature. So we have a negative feedback of low clouds. However, a warmer atmosphere may also produce more high clouds, like cirrus, which trap much of the outgoing long-wave radiation, increasing temperature. So we have a positive feedback of high clouds. On balance, it is believed that the negative cloud feedbacks win over the positive feedbacks. But scientists are still working to understand these feedbacks further. The overall effect of the feedbacks we have discussed is positive and serves to increase the warming due to increased greenhouse gas concentrations beyond what would be expected purely from greenhouse gases alone. For example, a doubling of carbon dioxide concentrations in the absence of feedbacks leads to approximately 1.25 degrees Celsius warming. Our best estimates indicate that the positive water vapor feedback would add about 2.5 degrees Celsius additional warming, while the positive ice albedo feedback adds about 0.6 degrees warming. While more uncertain, the negative cloud radiative feedback leads to just under 2 degrees Celsius cooling. Add up the numbers, and the total comes to about 2.5 degrees Celsius warming, double the warming that would occur without feedbacks. Understanding these positive and negative feedbacks is essential to increasing our confidence for global temperature changes in the future.